What's up, everyone? Welcome back. Patrick here, moving on to the next example dealing with polynomial functions in advanced functions. So we got these three polynomials here and we have to factor them. So starting with part A, we got y is equal to negative 3x to the 5 plus 9x cubed plus 6x squared. So first thing you always check is, can you take out a greatest common factor? And notice that in this case, you can take out a negative 3. I'm going to take out a negative 3 because this leading coefficient is negative. And then notice between the x to the 5x to the 3x squared, I could take out a x squared. And so what would I be left with? I'd be left with x to the 3 minus 3x minus 2, like that, right? And so now we have this simplified polynomial in this bracket. So I'm actually going to take that polynomial to the side. So let's call it like g of x. And I'm going to factor that. And then whatever this factors into, we'll bring that back into our main work for our final answer. So what we do here is we got to do factor theorem, right? So we got to test a bunch of numbers. So let's first try out 1. Right? If we plug in 1 here, is it going to give us 0? Well, we would have 1 minus 3 minus 2, which would give us negative 4, like that. And then negative 1, we would plug in negative 1 here. We'd have negative 1 to the power 3, which is negative 1 minus 3 times negative 1. So let's actually fully write it out. It would be what? Negative 1 minus 3 times negative 1 minus 2, which would be negative 1 plus 3 minus 2. Which would indeed give us 0. Okay, so from here, because g of negative 1 is equal to 0, we know by the factor theorem that x plus 1 is a factor of this polynomial here. And so now what you want to do is you want to take that polynomial and then divide it by that factor that you found. And you could use synthetic division because it's linear, or you could use long division. Personally, I prefer long division, so I'm going to do that. But no matter which division you use, make sure you're always getting a remainder of 0 at this step, because you should be getting a remainder of 0 because it's a factor. And whenever you divide by a factor, by the factor theorem, the remainder should always be 0. So let's rewrite this polynomial here. Now notice that there's no x squared. So we would have to put a placeholder there of 0x squared. So just be on the lookout for that as well. And from here, x goes into x cubed, x squared times. Then we'll have x cubed plus x squared. Subtract these over here. And then we would have negative x squared minus 3x. And then x goes into negative x squared, negative x times. We'll have negative x squared minus x. And then this would end up being negative 2x. Let's bring the negative 2 down. And then x goes into negative 2x how many times? Negative 2 times. And then we would negative 2 times x plus 1. We get negative 2x minus 2. I'm running out of room here. And so the remainder there would be 0, right? If we subtract these, right? So as expected, we got this remainder of 0. And so basically, what's happened, so let's erase a bunch of stuff here, is we took this polynomial, which we called g of x, and we've been able to factor it into x plus 1 and this quotient here, x squared minus x minus 2, like that. And so from here, all that's remaining to do is to factor that remaining quadratic right here. Okay, so factoring that quadratic would be what? X plus 1, and then this would end up being what? X minus 2, x plus 1. I'm not going to go through the process of decomposition on that. If you want to do that, get some practice in on the side. Just make sure that you are getting that value right there. And then notice the x plus 1s are actually the same. And so we could, in a nicer format, rewrite this polynomial as negative 3x squared, x plus 1 squared, x minus 2. And then that right there ends up being the factored form of this original polynomial in part A. Moving on to part B here, we got y is equal to 8x to the 5 plus 24x to the 3 plus 18x. So same thing as usual. Let's see if we can initially factor something out. Well, between the 8, the 24, and the 18, I can definitely take out a 2. And then notice that there is an x variable common in all the expressions as well. So I could take out the one with the lowest exponent, which is this x to the 1. So if I take out a 2x from all these, right, dividing all these expressions basically by 2x, what would I be left with in the brackets? We'd have 4x to the 4 plus 12x squared plus 9, like that. And so we're left with this quartic function in brackets here. Now this one's going to be a little bit unique, so I'm going to take this one, let's rewrite it over here, and let's deal with it separately. Now this one is tricky because this one, it actually does factor, but you can't find any of the factors with integers. Okay, which sounds a little bit weird. It's why I wanted to go through this kind of example in case you maybe run into it. It's a very rare example, but it can happen. There's actually no integer x value that you could plug in here that's going to make this 0. Okay, so you can't factor this with the factor theorem. And what you have to recognize here is that you got an x to the 4 and an x squared. So we could rewrite this x to the 4 as x squared squared, and then this is 12x squared plus 9. And then we could introduce a new variable, and we could let m equal x squared. So this would be what? 4 in this bracket, x squared. I'm going to put this m instead, so we'd have 4m squared plus 12m plus 9. And so from here, let's factor this. I'm going to actually go through the entire decomposition process on this one. So 4 times 9 is what? 36. That's the AC value. And then the B value is what? 12. And so two numbers that multiply to 36 and add up to 12, that's going to be 6 and 6. Right? So we would decompose this middle term into 6m plus 6m plus 9. And then what can we take out of the first two? We could take out a 2m. What would we be left with? 2m plus 3. What can we take out of these two? We could take out a 3, and we'd be left with 2m plus 3. Then we could take out a 2m plus 3. And what are we left with? 2m plus 3. And so that right there is actually a perfect square trinomial. So it ends up being, let's actually write it above here. This ends up being 2m plus 3 squared, but we can't just leave our final answer in terms of m because our original polynomial was in terms of x. So I would bring in this x squared now for this m, and it would be 2x squared plus 3 squared, like that, right? So that's the factored form for this, or for this bracket that was remaining. And so going back to our main work here, final answer would be 2x, and then we'd have this 2x squared plus 3 squared, like that. And to get this factored form of this bracket, this is pretty much the only way, at least that I know of, that you can do it. You can't do this with the factor theorem, and I'm going to show you why quickly in case you're interested, is because, okay, let's say that I gave you this factored polynomial, and I asked you to get the x-intercepts of it. Well, over here we'd have an x-intercept of 0. Well, how would we get the x-intercept here? We would have to make this factor equal to 0 and then solve for x. Well, notice we'd end up with x squared equals negative 3 over 2. You can't square root a negative, right? And so there would be no real numbers that are intercepts coming from this factor. And so the factor theorem wouldn't work, right? So if you tried to plug in like plus or minus 1 into these x values, plus or minus 2, etc., 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 you wouldn't be able to get a number, right? So this one's a little bit more tricky. You'd have to take this polynomial, recognize it that you could convert it to a quadratic, factor that quadratic, which would be a perfect square trinomial, with like another variable, with that change of variable, and then bring back that x squared. And then you'd end up with this. All right, so pretty unique question. Again, it's fairly rare, but I did want to throw it in as an example so you could see potentially different polynomials that can come up in this unit. Yo, what's up? Quick little intermission here. Wanted to mention a few things quickly and we'll get right back into the question. First off, if you are getting value from this video, if you can please like the video and subscribe to my channel, it does help me out a lot. Number two, if you're watching this on YouTube, you can go to the description box and there is a link that will take you to my website, allthingsmathematics.com, where all my courses are organized so you can watch the videos in order, and I'd recommend doing so because lots of concepts carry over from one video to the next. Also, for lots of the courses, at the end of the chapters, you can find tests that you can practice with, and the tests have video solutions as well. Number three, if you feel like you need personalized help in tutoring, give me a shout. I currently tutor students 7 days a week over Zoom, both high school and university students, one-on-one and in groups. You can text me. We can discuss availability and then we can book a session. My contact details are on my website. And lastly, feel free to forward the website to any of your friends who are also taking the course, who you feel can benefit from these videos as well. Hit me up on all my socials. It's All Things Mathematics for all of them. Back to the video we go. Now moving on to the last one, part C. We got y equals 12x cubed plus 4x squared minus 17x plus 6. So what's the first thing we always check for? Can we take out a greatest common factor? Well, between 12, 4, negative 17, and 6, can't take anything out of those. And then notice that this 6 constant, it doesn't have an x variable. Okay, so we can't take anything out of the polynomial initially. And so we'd have to go into factor theorem. Now this one is a little bit tricky as well. If you tried to plug in like different integers, so like -1, +1, -2, +2, etc., there would be no integers that would make this equal to 0. And so for this particular one, you would have to actually factor it with the rational zero theorem that we've gone through before. And if you remember, what that means is that like potential factors for a polynomial in standard form is always going to be factors of the constant, which is 6 in this case, over factors of the leading coefficient, which is 12 in this case. So what are the different factors of 6? Well, plus or minus 1, plus or minus 2, plus or minus 3, and then plus or minus 6, all over. Factors of 12 would be what? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12, right? So there's a lot of factors to try out. And as I mentioned, this is one of those where unfortunately there's no integer that's going to work out. Now, most of the time, you are going to at least have one integer that's going to make the polynomial equal to 0. But you might run into a polynomial, your teacher might throw one on the test, where there won't be any integers that work, such as this one over here. And so you'd have to try out these other factors. So as I said, we could pretty much forget about this plus or minus 1 in the denominator because I told you there's no integers, so it can't be like plus or minus 1 over 1, right? Or plus or minus 2 over 1 or -1 because those will all be integers, right? And so you have to start checking these different fractions. So notice that plus or minus 1 over 2, that's a potential factor, or you could have plus or minus 1 over 3, right? Plus or minus 1 over 4, plus or minus 1 over 6. Okay, these are all potential values or intercepts of this polynomial. that when you plug it into the x values, it's going to make it equal to 0. And then you could have like plus or minus 2 over 3, or plus or minus 2 over 4, which actually simplifies to plus or minus 1 over 2. So sometimes there's going to be like overlap, so you could skip certain scenarios. So this one's a bit of a pain. You're going to have to test out a bunch of these different fractions. But the fraction that is going to work is going to be positive 1 over 2. Okay, so if we took this polynomial, let's say it was like f of x, if you plugged in 1 over 2 for all the x values, that would make it equal to 0, which means that what? What is the factor going to be? If f of 1 over 2 is equal to 0, that means the factor, one of the factors, is 2x minus 1. Right? If we were going backwards, if this was like a factor in a polynomial, the x-intercept would be positive 1 over 2. Well, now we're just going backwards. We found that x-intercept, and now we're creating the factor. So since f of 1 over 2 is equal to 0, 2x minus 1 is one of the factors. But what's nice about this is just a cubic function. So once we find one of the factors and we divide that cubic function by that factor, then we know our final quotient is going to be a quadratic, which we can then use decomposition on to find the other two factors. So it's if you're given a cubic and there's no integer factors, it's all about finding that first one, and then the process is a little bit easier. Now, if it was a quartic, then you'd have to find 2 of these before you got to a quadratic with long division. But luckily, we were given a cubic here. And so let's divide this, see what we get. So we got 6x squared, right? 2x goes into 12x cubed, 6x squared times, and then this would be 12x cubed minus 6x squared. Subtract these, this would be what? 4 minus negative 6, which is 10x squared minus 17x. 2x goes into 10x squared 5x times. And this would be 10x squared minus 5x. Subtract these, and we'd get what? Negative 12x. Bring this positive 6 down. And then 2x goes into negative 12x, negative 6 times. And so we would have negative 12x plus 6, subtract these, and we would get a remainder of 0 as expected, right? Because we were saying that 2x minus 1 was a factor. Well, if 2x minus 1 is a factor of this polynomial, when we divide it, we should be getting a remainder of 0 always. All right, and so now all that's remaining is basically we just got to factor that quadratic that is left over. So let me erase some stuff here, kind of clear this board off. And now let's just take this remaining quadratic that we got. I will bring it down here. And we just got to factor that. So two numbers that multiply to 6 times negative 6, which is negative 36, and then add up to 5. What would that be? That would be negative 4 and 9. I think that works, right? Negative 4 times 9 is negative 36. Negative 4 plus 9 is positive 5. Decompose that. Minus 4x plus 9x minus 6. We could take out from these two a 2x, so we'd be left with what? 3x minus 2. From these, we could take out a 3, 3x minus 2, and then we could take out a 3x minus 2. And we'd be left with what? 2x plus 3, like that. Right? So those are the remaining factors. And notice that, again, none of these factors give us an x-intercept that is an integer, right? All the x-intercepts would be fractions. 1 over 2, 2 over 3, negative 3 over 2. So when you're doing the factor theorem, you would have to be able to get one of these factors, right? To test out and make the function equal to 0 using that rational 0 theorem, right? Factors of 6 over factors of 12. And you'd have to test out the different fractions until you got one that would make it equal to 0. Okay, so another rare example. There isn't too many like this where you're not going to have any integer intercepts that you can use, but I have seen teachers throw these kinds of polynomials on where all of the factors are fractions, and so they're testing you on using the rational zero theorem and then being able to potentially find one of these factors and then go through the process. All right, so just be on the lookout for these as well. They may come up, but nevertheless, this is what the polynomial factors to. And that's a wrap for the video. Hopefully you enjoyed that. If you want to see more videos like this, please go to my website, allthingsmathematics.com. Over there, all of the videos are organized by chapter, by section. If you feel like you need tutoring at any point, you could also hit me up. My contact details are on the website. Enjoy your day, and I'll see you in the next one. Peace out.